Greetings, salutations, all those nice things. Welcome to the very last lesson in this second unit on trigonometry. Today we're going to be looking at the law of cosines. As we recall, with this unit, we've been looking at triangles that are not right triangles. With right triangles, we could use that SOHCAHTOA business. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tan is opposite over adjacent. That only applies to right triangles. So we had the law of sines, which was very useful. It's another tool in the toolbox, and it helped us solve some triangles where certain information was known. But look at these two triangles. With these two triangles, the law of sines cannot be used. Take a moment, take like 15, 20 seconds, consider that, look at why that is, hypothesize something, and whisper it to the people around you to see if they concur. As I imagine you've all been whispering to each other, there's no pairs of side and angle opposites. Right? In this, that's a selection there. In this first triangle, we don't have any angles at all. So if we're trying to plug things in to sine A over A equals sine B over B, well, there's two unknowns because we don't know any of the angles. Similarly, if we look at the other triangle, there's no matching side angle pair. So this 17 isn't opposite a known angle. This 20 isn't opposite a known angle. And the one known angle isn't opposite a known side. So there's not enough information for us to be able to use the law of sines. Thus, we need another tool in our toolbox. And that's the law of cosines. The reason we can't solve those triangles with sine law is we don't have any pairs of sides with opposite angles. Yeah, you take a moment to write that down. I'm going to take some water. So we're going to develop the law of cosines. As with the law of sines, it is required to prove. So it is considered fair game for you to be asked to prove the law of sines or law of cosines on a test or quiz or any kind of assessment. So make sure you do know it. There is some preliminary work that has to be done for us to develop the law of cosines, but all of it is part of the proof. So looking at this particular triangle here, we're going to look at a few aspects. We're going to look at cosine of angle A, and that's based on this right triangle we've kind of created within the given triangle. If we look at that, if we look at cosine of A, well, since that highlighted triangle is a right triangle, we can simply use our SOHCAHTOA stuff and say that cosine of an angle is adjacent over hypotenuse. So cosine of A is x over c. And if we rejig that a little bit, isolate x, we're going to multiply both sides of that by c. So x is equal to c times cos A. And that is that part done. We're also going to use that triangle with finding h squared. We can use the Pythagorean theorem. Excuse me, sorry. Pythagorean theorem says the sum of the squares of, the sum of the squares of the two adjacent sides will be equal to the square of the third side. Only for right triangles, but hey, that is a right triangle. So x squared plus h squared equals c squared. If we rearrange that a little bit, we can say h squared is c squared minus x squared. And that's the preliminary work, which, again, is part of the whole proof. So still needs to be shown, can't be taken as a given. Does need to be written when you are writing the proof out. The rest of the work comes from looking at the other right triangle here and starting with the Pythagorean theorem for that particular triangle. A squared is equal to the sum of the squares of the perpendicular sides. So it's the square of this side, which is h, and it's the square of this side. Both of those come together. So we've got to add in the square of that b minus x. I'm going to do two things in the next step. One of them is swap out this h squared, because we know that h squared is equal to c squared minus x squared. So I'll fill that part in. A squared is, instead of h squared, writing c squared minus x squared. The other thing I'm going to do is expand and simplify the square of that binomial. So b minus x squared is the first thing squared plus the second thing squared, and then minus 2 times their product. So those are the two components. This h turned into this c minus x. This b minus x squared turned into b squared minus 2bx plus x squared. We can do some things from here. For starters, there's these common x squareds. One's subtracted, one's added, so they cancel each other out. Beyond that, I'm going to do just a little bit of rearranging. So I'm going to write the b squared first, the c squared second, and then there's this remaining term, minus 2bx, minus 2bx. And the last step of this proof requires us to go back to the preliminary work, because we're going to have this in terms of a's, b's, and c's. There's an x in here, but we know that x is the same thing as c cos a. So that's what we fill in last. A squared is b squared plus c squared minus 2b times c cos a. Again, replacing x with c times cos a, because that's what we know it to be. That is the law of cosines. It's written in such a way that we can find the side opposite an angle given, or if we rearrange this, we can find an angle given we can find an angle that's opposite a given side. But it depends on the context we have for what we're actually trying to find. Now, this is for triangles that involve a's, b's, and c's. Triangles might not involve a's, b's, and c's, but we kind of want to keep this whole thing in our head brain. And we can write it down on a scrap piece of paper or something. But if we're dealing with a triangle that does not have a's, b's, and c's, we can't use a formula that has a's, b's, and c's. Like this. This triangle has a T, a U, and a V. And we need to find the length of the missing side. So we need to find this, which is side T, being opposite angle T. So instead of the cosine law as it's written in our head brains as a squared equals b squared plus c squared minus 2bc times cos a, we're going to rewrite that as t squared equals the sum of the squares of the other two sides. So instead of b squared plus c squared, we'll have u squared plus v squared minus, instead of 2bc, we'll have 2uv. And instead of cosine of angle A, the angle we're using here is t, opposite the side we're trying to find. So cos t. It's not super necessary to write down that step, but I find it can help frame what we're about to do. So it's a good thing to throw in there. From here, subbing in all the things we know. t squared is u squared, u is 9, plus v squared, where v is 7, minus 2 times u times v times cos of that angle of 60 degrees. At this point, I would jump to the calculator. I would plug in all this exactly as it's written, making sure your calculator's in degrees mode so that it computes that value properly. If we plug all that into the calculator, we get that t squared is 67. Therefore, t is equal to one particular thing. Note, we're dealing with real triangles, so we can't have a negative value for a length. We're not going to go plus or minus root of this value. So just straight up positive root of 67. Should be a little bit more than 8. Make sure you can get that in your calculators, and it's, according to mine, 8.2. Are there any questions, comments, concerns? Well, seeing none, I recommend trying the next two examples. So pause this video right after I finish speaking, try those examples for a solid, 5 minutes, and then resume the video where I'll fill those in. And we're back. Hopefully you've given it 5 minutes and you've tried these examples. I'm going to now. We're missing side F. So I'm going to write that F squared is equal to d squared plus e squared minus 2de times cos big F. From a variables and notation standpoint, make sure you're using the proper case letters. Remember that lowercase is for sides, uppercase is for angles. And then filling in what we know. F squared is 8.5 squared plus 11.1 squared minus stuff. 2 times 8.5 times 11.1 times cosine of 100 degrees. You're going to get a non-terminating decimal in your calculator. I'm getting that as approximately 228.227 and then a bunch of other numbers. When you take that final step, keep this number in your calculator exactly as it is with its bajillion decimal places, and just use your calculator to find the square root of the previous answer. Use that answer button on your calculator or whatever however you access the last known or used number. So square root of that number is, to the nearest tenth, approximately 15.1. If you do round it a bit too early, you might be slightly off. That would cause an error in your final answer, which would just be a rounding communication error, but still best to be avoided if you can. Last one here, we are after side P. P squared is q squared plus r squared minus 2 qr cos big P. P squared is q is 13.4, r is 5.9. Oopsie daisies. My angle is 75. Here I'm getting 173.445 and then some other numbers. She'll actually be 3 dots there. And again, keeping things as exact as possible. just taking the square root of that full number that appears in your calculator, not this one with only a few decimal places, just in case. I'm getting that P is about 13.2. So that's using cosine law to find an unknown side. And that's kind of like the case on the first page over here. Again, we didn't have a pair of side angle opposites, so we needed to find that, or we needed another tool in the toolbox, and that was cosine law. The other case where it applies is this, where we are given three sides but no angles. So when those three sides are all together, they're pretty locked in. Can't shift. A triangle is a very rigid, sturdy structure. So cosine law can be rearranged so that the angle is isolated, which we'll do. So the cosine law itself says a squared equals b squared plus c squared minus 2bc cos a. If we want to have this such that the angle is isolated, I'm going to basically move this thing to the other side, only because that way, instead of having a negative coefficient, it's going to have a positive one. At the same time, I'm going to take this a squared and move it to the right side. So my first step here is to say that 2bc cos a is equal to b squared plus c squared minus a squared. I'm just going to rewrite that a bit more neatly. Beautiful. Getting this so that the cosine of A is isolated means addressing this 2bc that's in front of things. So I'm going to divide the left side by 2bc, which means I'm going to divide the right side by 2bc. That tells me that cos A is equal to b squared plus c squared minus a squared all over 2bc. Make my c better. So this is another version of the law of cosines. It's just a manipulation of the other one we had. You can feel free to memorize this version. Personally, I've only got so much storage space in my head brain, so I always memorize this one. And then if I need to get the other one, I can just follow these two whole steps to get that. So that's my recommendation. We're going to use this to find angles. Again, now this is in terms of A's, B's, and C's, not everything that we work with. Excuse me. Sorry. We'll have A's, B's, and C's, so we're going to have to be able to pick apart what's what. Looking at this angle that we have, A, matches with whatever we're subtracting in this numerator. The other components are the other two sides, and then those other two sides are also what's in the denominator. So that can kind of help frame what we're working with. In this case, we're finding angle y. We can say that the cosine of y is equal to some manipulation of the cosine law. Since we're dealing with angle y, we're also going to be subtracting side y. That means that the other two sides, x and z, are filling in these other parts of the formula. So we've got x squared plus z squared minus y squared on top, and that all gets divided by 2xz. At this point, we're just substituting in. Cosine of y is 6 squared plus 5 squared minus 8 squared all over 2 times 6 times 5. Do be careful when you're punching this into your calculator. It's very easy to make mistakes if your calculator doesn't display this as a fraction. So my recommendation is when you're putting it in, just make sure there's brackets around your numerator, which would probably be round brackets in your calculator, and make sure there's brackets around your denominator as well, just to make sure you get a proper value back. In any case, what you should be getting in your calculators is about negative 0.05. And then taking whatever result in our calculator, taking the inverse cosine of it, directly gives us an angle of 92.7 degrees. Note, we're not looking at taking a quadrant 3 angle. Yes, cosine's negative, that's true, which means that y could be in quadrants 2 or 3, but this is a triangle. And a triangle can't have any angle be more than 180 degrees because the sum of the angles in a triangle is 180 degrees. So to keep things real, this is all we do. Boom, calculator done. That's that. I dare to try the other example. So pause this video after I stop speaking. Pause it for a solid, 3 minutes. And then resume to check your work. And we're back. Hey, this triangle does have A's, B's, and C's. Maybe I'll start writing things as cosine of A equals some stuff. Just kidding. I won't. Because A is not the angle we're trying to find here. We could find angle A. I'm sure the work we would do to find it is all correct, but it is incredibly irrelevant here because we need to find angle B. So, setting up this formula, we're saying that, cosine of B is equal to something. It's some fraction. At the end of the fraction, we are subtracting B squared in the numerator, which means A's and C's make up the other parts of this. So A squared plus C squared minus B squared on top. And then that A and C come into the bottom as well. So there's our manipulation of the cosine law for this particular purpose. Filling things in. We get that. I guess we should have talked about mark values for all these questions. These are all 2-mark questions, straight up. One of the marks is for correct substitution into an appropriate formula. So that's worth 1 mark right there. The other mark is the computation from there to find the value of B. You do not get any marks for evaluating that fraction in your calculator and finding out that cos of B is approximately 0.7089 and then some other some other numbers, because that's not like using your calculator properly is not a skill being evaluated. But finding an angle from a ratio is. So taking inverse cosine of both sides, we get that B is 44.8 degrees. And that one is DU and done. So that is the end of this lesson. That's also the end of the topic. Whoa! So we're going to spend a little bit of time just making sure we're feeling confident with when to use law of sines, when to use law of cosines. Going back to that ambiguous case stuff in 5.3. But all of that will have a place on a test to start thinking about when an appropriate quiz date is for parts 1 to 3. And that's my whole story. Be good to yourselves, be good to one another, and tell everyone I say hello.